Morning, all. So we can go over problems on the review sheet for the midterm. And there are a lot of problems, so I'm happy to go over whichever ones you ask about. Any preferences?
Shall we go over everything, Professor? So that will do like a review for us.
Well, I can't get through them all in one class, but I'll start.
Okay.
So let's start with number one. So suppose G is a group which consists of four elements. This is a cyclic group of order 4. So a to the fourth is going to be the identity. So we sometimes write this as A with brackets around it. This means the cyclic group generated by A. It's the set of all powers of A. But if A to the fourth is equal to E, then these are the only distinct powers. And so the order of G is 4. And by Lagrange's theorem, the order of any subgroup H of G divides the order of G. So whatever the order of H is, H divides 4. And the only divisors of 4 are 1, 2, or 4. So a subgroup cannot have 3 elements. It can only have 1, 2, or 4 elements. So one subgroup is the trivial subgroup, consists just of the identity. And of course, in this case, this order is 1. And another subgroup, H, is the whole group. So the order of H is 4. So if there is any other subgroup, it has to have order 2, and it means it has 2 elements. So if I take H to be A, E, the identity, in A squared, this is a subgroup of order 2, because this is closed under multiplication. In fact, the multiplication table would be EA squared, EA squared. E times E is E times A squared is A squared. A squared times the identity is A squared. A squared times A squared is A to the fourth, which is the identity. So this is a subgroup of order 2, and it's the only subgroup of order 2, because if a subgroup contained A, it would be the whole group. And if a subgroup contained A cubed, which is A inverse, it would also be the whole group. So this group has exactly 3 subgroups: the 2 trivial subgroups, the identity and the whole group, and one subgroup with 2 elements. Any questions about that? Okay. Problem 2, we take the cycle 1, 2, 1, 4, 2, 3 in the symmetric group S4. If I want to write sigma as a product of transpositions, there are many ways to do it, but the simplest is, as it turns out, 1, 4, 4, 2, 2, 3. So this is a product of 3 transpositions, and you can check. This sends 1 to 4, 4 to 2, 2 to 3, 3 to 2 to 4, back to 1. So that's sigma. All right. As I'm going through this, just interrupt me if you have any questions. Sigma squared is sigma times sigma. That's 1, 4, 2, 3 times 1, 4, 2, 3. Again, these are functions. Composition of functions. This sends 1 to 4 to 2. So 1 goes to 2. 2 goes to 3, goes back to 1. See, 3 goes to 1, goes to 4. 4 goes to 2, goes back to 3. So sigma squared is a product of two transpositions. And sigma inverse, well, let's see, let me write this in standard form. If sigma sends 1 to 4, the inverse sends 4 back to 1. If the inverse sends 4 to 2, the inverse sends 2 back to 4. If the inverse sends 2 to 3, the inverse sends 3 back to 2. And if the inverse sends 3 to 1, the inverse sends 1 to 3. So this is sigma inverse. Or if I write this as a 4 cycle, 1 goes to 3, goes to 2, goes to 4, goes back to 1. Okay? In problem 3, we have two permutations in S5. So sigma tau, what is sigma? In standard form, is 23514. And what is tau? In standard form is 45213. So what is this permutation in standard form? 1 goes to 4, goes back to 1. 2 goes to 5, 5 goes to 4. 3 goes to 2, 2 goes to 3. 4 goes to 1, 1 goes to 2. 5 goes to 3, 3 goes to 5. So this is the permutation in standard form. In fact, this is really just the transposition 2, 4, but that's the answer. And if I compute tau sigma, so tau is 45213. Sigma is 23514. So this sends 1 to 2 to 5, 2 to 3 back to 2, 3 to 5 back to 3, 4 to 1 to 4, 5 to 4 to 1. So this permutation fixes 2, 3, and 5. In fact, this is just the transposition 1, 5. So that's what it is.
Professor, that the smallest number k, positive integer k, such that the sigma k is the identity permutation.
Oh, sorry, in problem 2?
Yeah,
Okay.
C one.
So this is sigma. This is sigma squared. If you compute sigma cubed, you will not get the identity, but sigma to the 4th is the identity. So the smallest power of sigma, which gives you the identity, is 4. So this permutation has order 4.
Okay, thank you.
Problem 4. We have a 10 site. We have a permutation in S10, 7, 5, 10, 3, 8, 9, 1, 6, 2, 4. And I want to write this as a product of disjoint cycles. So let's start with 1 and see where it goes. 1 goes to 7. 7 goes back to 1. Okay. What about 2? 2 goes to 5. 5 goes to 8, 8 goes to 6, 6 goes to 9, 9 goes back to 2. See, I haven't used 3 yet. 3 goes to 10, 10 goes to 4, 4 goes back to 3. So this permutation is a product of 3 disjoint cycles, a 2 cycle, a 5 cycle, and a 3 cycle. All right. Any questions about these? All right. Number 5. We want to prove the set 2, 3 generates the additive group Z. So the subgroup generated by 2 and 3, this is everything you can get by looking at all sums of multiples of 2 and multiples of 3. This is everything of the form 2x plus 3y for any integers x and y. Right? That's what it means when you look at the subgroup generated by a set. If it's written additively, it's the smallest subgroup that contains 2 and 3. If it contains 2, it contains all multiples of 2. If it contains 3, it contains all multiples of 3. It's closed under addition, so it contains all multiples of 2 and 3. And you can notice that 1, for example, is 2 times minus 1 plus 3 times 1. So this 1 is in this subgroup. Let's call this H. So this is in H, but H is closed under addition, so all multiples of 1 and their inverses, all multiples of minus 1, are in H. So this subgroup H generated by 2 and 3 has to equal the whole group, right? So of course, you need to write this down in words, right? So this subgroup contains 1, and the subgroup generated by 1 is all of Z. So the subgroup generated by 2 and 3 is not a proper subset or subgroup of Z, it's the whole thing. And problem number 6 is similar. If I take the subgroup generated by the numbers 6, 10, and 15, these numbers are relatively prime. And in fact, I can write 1 as 6 plus 10 minus 15. So 1 is in the subgroup generated by 6, 10, and 15, which means this has to be the whole group of integers. Okay. Questions about this? Let's see, number 7 is to prove that no finite subset of the rational numbers Q generates Q. So this says if you take a finite set of fractions and you look at the subgroup they generated, that is all sums of multiples of those finite set of fractions, you'll never get every rational number. So suppose we take a finite set of fractions. So suppose we take P1 over Q1, P2 over Q2, let's say PK over QK. So this is a finite set of rational numbers. It's just another name for fractions. Suppose I take a common denominator, Q, common denominator. So I can write this as a set of fractions, all with denominator Q. So I can write this as capital P1 over Q, capital P2 over Q, capital PK over Q. Because they teach you in elementary school that every set of fractions, there's a common denominator, the least common multiple, for example, or even just the multiple. If I take the product of all the denominators and call that Q, that's a common denominator for these fractions. So if I have any finite set of fractions, I can always write them with the same denominator and different numerators. But if you take fractions with denominator Q, all the same, capital Q denominator, you add them, you're going to get another fraction with the same denominator. And when you subtract them, you're going to get another fraction with the same denominator. So this generates a subgroup with all denominators Q. Because you get the subgroup they generated by just adding and subtracting these numbers. So for example, 1 over Q plus 1 is not, let's call the subgroup H, is not in H. So if you have a finite set of fractions, you can write them with the same denominator. The subgroup they generate is going to be a set of fractions with the same denominator, Q. So for example, the fraction 1 over Q plus 1 is not in this, can't be written as a fraction with denominator Q. So H is not all rational numbers. That's a proof. Right. Again, you might have to think about this a little bit. You should. But this is one way to prove this statement. Right. Problem number 8. So we have subgroups H1 and H2 of a group G. We want to prove that the intersection, what is the intersection of two sets? It's all X in G such that X is in H1 and X is in H2. We want to prove the intersection of two subgroups is another subgroup of G. So it's like if this is G, here we have H1, here we have H2. That's the intersection. And we want to prove that's a subgroup. Let me call this intersection H. So a subgroup of a group is a subset that has three properties. It contains the identity, it's closed under multiplication, and it's closed under taking inverses. So if the identity is denoted by E, we have E is in H1 and E is in H2 because these are subgroups. Subgroup always contains the identity. So if E belongs to both of these sets, E is in H1 intersect H2. So that's the first property of a subgroup, and it's satisfied. Suppose X is in H1 intersect H2. That means X is in H1 and X is in H2. That's the definition of intersection. But if X is in H1, X inverse is in H1 because it's a subgroup. Right? Subgroup contains the inverse of each element. Similarly, x is in H2 implies x inverse is in H2. But if x inverse is in both of these sets, then x inverse is in the intersection. So this intersection is closed under the operation of taking inverses. And third, suppose I take two different elements, x, y, and H1 intersect H2. So x in H1 implies, sorry, so x is in H1 intersect H2. So x is in H1 and x is in H2. And y in H1 intersect H2 implies y is in H1 and y is in H2. But if x and y both belong to H1, then x times y is in H1 because H1 is a subgroup, it's closed under multiplication. And if x is in H2 and y is in H2, xy is in H2. Again, H2 is a subgroup, it's closed under multiplication. So the group element xy belongs to both H1 and H2. So xy is in their intersection. And that's the third condition of a subgroup, and we just showed that it's satisfied. Questions about this? By the way, this is just a reminder, because I've said this in class a couple of times. It's not on the review sheet, but the proof of Lagrange's theorem in whole or in part will be on the midterm. It's a fundamental result in algebra that you absolutely have to learn in this course. Okay. Anyway, continue. Problem 9. So if you have U, a 2 by 2 matrix, A, B, C, D, the determinant of U is AD minus BC. And a V, E, F, G, H is another 2 by 2 matrix. The determinant of V is EH minus FG. So you've taken linear algebra, so you're familiar with matrices, certainly. What is U times V? A, B, C, D times E, F, G, H. If you multiply the two matrices together, you get AE plus BG, AF plus BH, CE plus DG, CF plus DH. So the determinant of UV, it's this times this, minus this times this. So you just have to multiply this together. So now you do high school algebra. You just multiply this together. There'll be some cancellation. And eventually you show this is the same as AD minus BC times EH minus FG, which is the determinant of U times the determinant of V. So that's all you have to do. It's just, you have to know high school algebra, multiply this out. There'll be some cancellation. You'll be able to factor it and you'll get this. Okay. Any questions about that? Problem 10. I have what is called GL2R. So this is the set of all 2x2 matrices, A, B, C, and D in M2 of R. This means 2x2 matrices with the numbers A, B, C, and D, real numbers. And I'm looking at all matrices that have the property that AD minus BC is different from 0. So I'm not looking at all matrices. I'm looking at all the matrices with non-zero determinant. And I want to show this is a group under matrix multiplication. So first of all, this is a check. So you have to do a calculation. If you have three matrices, say X is A, B, C, D, Y is E, F, G, H, Z is, say, K, L, M, N, you just have to check. You have to compute. X times Y times Z is X times YZ. So this is literally just a long multiplication using high school algebra. So I'm not going to do it. You multiply X and Y, you get a matrix multiplied by Z. Multiply Y and Z, you get a matrix, multiply on the left by X. Show you end up with the same matrices in both cases. So this is a long calculation, but that's part of it. Second, if I take the matrix 1, 0, 0, 1, oh, and by the way, first we have to show this is closed under multiplication. So if the determinant, so here I have matrices X and Y. If X is in GL2R, then the determinant of X is not 0. If Y is in this set of matrices, then determinant of Y is non-zero. We just proved in the previous problem that the determinant of XY is the determinant of X times the determinant of Y. And these are non-zero numbers. The product of two non-zero real numbers is non-zero. So X times Y is in GL2R. So this is very important. This says that this set of matrices is closed under multiplication. This says it's associative. This is the identity. If you take IX or XI, you get X for all matrices X, in particular, all the matrices in GL2R. And the third is every matrix in this set has to have an inverse. If X is A, B, C, D, you can check that X inverse. So in this case, the determinant of X, AD minus BC, is not 0. So you can divide by it. So in high school algebra or linear algebra, you learn that I think D minus B minus CA, if I multiply these two matrices together, I get almost the identity. It's a diagonal matrix. Suppose I call this number delta. So delta is the determinant. This over delta, D over delta minus B over delta minus C over delta, A over delta. I can divide by delta because the determinant's non-zero, and you can check X inverse is the identity, and X inverse X is the identity. So this is a group. It's a set of matrices closed under multiplication that contains the identity and the inverse of each element. And how can I show this is non-abelian? Well, I can just So G is non-abelian if xy is not equal to yx. So this is GL2R. If for some, not for all, but for some x and y in the group. So let me just pick two matrices almost at random. Let's see, 2, 3, 1, 2. The determinant of x is 1. Suppose I let y be equal to, I don't know, let's try this, make it easy, 1, 1, 0, 1. So the determinant of y is also 1. So these are matrices in GL2R. So let's do the calculation. What is xy? 2, 3, 1, 2, 1, 1, 0, 1. When I multiply, I get 2, 5, 1, 3, I believe. What about yx? So I'm multiplying in the opposite order, 1, 1, 0, 1, 2, 3, 1, 2. When I multiply, I get 3, 5, 1, 2. This matrix and this matrix, they're different. So these are not equal. Therefore, G is not abelian. Okay? All right. What about number 11? So the subgroup H of a group G is normal if it satisfies the following condition. Let's see. There are several ways to.
And left coset and the right coset are equal, then we can say it's a normal group, right?
Right. So that's one definition. That's actually the definition I like, but I
And
think the book
conjugate.
starts with an equivalent definition, which is the following. So if, let me just write this. If the left coset xh equals the right coset hx for all x in the group. So that's an easy way to write this. So what is xh? Xh is the set of all elements x times h, where h runs through all the elements of the subgroup H. And Hx is the set where you multiply every element of H on the right by X. So if G is abelian, XH equals HX for all X and G, H and H. So then these two sets are the same. Because this element equals this element if the group is abelian. So that's all you need to prove to say that every subgroup of an abelian group is a normal subgroup. Problem 12. is to look at a subgroup H2 of R, which is the set of all matrices 1B, 0, 1, where in GL2R, notice for this matrix, the determinant is 1 times 1 minus B times 0, which is 1, which is not 0. So this is a matrix in GL2R, and I look at all such matrices for all numbers B. And I want to show H2R is a subgroup. So the first thing I need to show is closed under multiplication. So suppose I take two such matrices, I'll call it 1A, 0, 1, and 1B, 0, 1, and I multiply them. What do I get? I get 1, A plus B, 0, 1. So again, I have a matrix with ones down the diagonal, 0 in the lower left corner, and some number in the upper right corner. So this is, again, an element of H2 of R. So this set of matrices is closed under multiplication. And the identity, well, again, to be in this subgroup, you need 1 down the diagonal and 0 in the lower left. So this is an H2 of R. And what is the inverse of 1A, 0, 1? It's 1 minus A, 0, 1. Because if you multiply them, you can check, you get 1, 0, 0, 1. And in the opposite order as well. So this set of matrices is closed under multiplication, closed under taking inverses, and contains the identity. So it's a subgroup. And it's abelian. Again, let me just write this down. I have 1A, 0, 1, 1B, 0, 1. That's 1A plus B, 0, 1. But A and B are numbers. A plus B is B plus A. So this is 1B, 0, 1, 1A, 0, 1. So the order of multiplication doesn't matter. This is an abelian subgroup. Right. Questions about that? Okay. Problem 13 is to state and prove Lagrange's theorem. So let G be a finite group. Let H be a subgroup of G. Let G colon H be the index of H in G, which is the number of left cosets of H in G. And the theorem says that the order of the group is the order of the subgroup times the index. Again, the index is, if you look at all of the left cosets, it's the number of left cosets. That's just a name for the number of left cosets. So that's Lagrange's theorem. And the way we proved it, we started off by proving two lemmas. So the first lemma says that left cosets of a subgroup H of a group G partition the set G. That is, they are pairwise disjoint and sort of cover G. All right, so this means that if you take two cosets, XH and YH, the intersection, so if the intersection is not empty, then in fact, these two sets are the same. It doesn't mean X equals Y, but this left coset and this left coset are the same sets. Okay. Also, X, which is X times the identity, is certainly in the left coset XH. So every element of the group is in some left coset. So the union of the left cosets is all of G, and the left cosets are pairwise disjoint. So that's the first lemma. The second lemma says that if H is finite subgroup, then the number of elements in XH equals the number of elements in YH for all X and Y in the group. And in particular, if we take Y equal to the identity, then the left coset EH is just H. And so the number of elements in every left coset is the same as the number of elements in this particular left coset, which is this subgroup. So the number of elements in the left coset of a subgroup is the number of elements in the subgroup. So these are the two statements you have to prove. The proof of this, by the way, there are lots of ways to prove it. One of the simplest is you can define a function f from h to xh by f of an element h is x times h. So this is 1-to-1 and onto. So this is a bijection, so 1-to-1 and onto function. So just this statement proves that every left coset has the same number of elements as the subgroup H. And from these, we can get very quickly the proof of Lagrange's theorem. Here we have G. G is finite. H is a subgroup. So we have all the different left cosets. There only can be finitely many. Every coset is a non-empty set. So you can't have infinitely many disjoint subsets contained in a finite set. So suppose the set of left cosets is x1h, x2h, up to x of kh. So the index of h and g is equal to k. So G is the union of these cosets, x1h, union x2h, and so forth, up to x of kh. And this is a partition. These sets are disjoint. So the cardinality of G is the sum of the number of elements in each left coset. But these all have the same number of elements, cardinality of H elements. And I have exactly K summands here. So this is K times H, which is the index of G and H times the cardinality of H. And that's the whole proof.
It is K times cardinality of H, right?
Yes. Because I have H left cosets. Each of them has size cardinality of H. So K times cardinality of H. And K is the index. Okay. Problem 14. So I have the group of integers z mod mz, or zm. This is the standard notation. This is the notation used in the book. This is the set of congruence classes mod m. So it's mz, 1 plus mz, 2 plus mz, and so forth, up to m minus 1 plus mz. And suppose that D divides M. So let's say M is D times Q for some Q. Take positive divisors to make it easier. So Q is M over D. So suppose I let H be the subgroup generated by Q plus MZ. This is a congruence class, right? So what is this? This is Q plus MZ, 2Q plus MZ, 3Q plus MZ. I'll get to D minus 1Q plus MZ. And the next element I get when I add will be DQ plus MZ. But DQ is equal to M. And M is 0 mod M. So this is MZ, which is 0 plus MZ. So here I have exactly D elements, and they form a subgroup. It's the subgroup generated by this one element. And the smallest multiple of Q, which is 0, is D times Q. So this is a subgroup of order D. For example, suppose I take M equal to 6 and D equal to 3. So 6 is 3 times 2. Q is 2. So if I take the subgroup consisting of 2 plus 6z, 4 plus 6z, and 0 plus 6z, or 6z, this is the subgroup generated by 2 plus 6z, and it has order 3. It has 3 elements. So 3 divides 6, and the integers mod 6 contain a subgroup with 3 elements. Right? That's all we're saying here. Any questions about that? Problem 15, we have disjoint cycles, sigma and tau in Sn, and we want to prove sigma tau equals tau sigma, that disjoint cycles commute. So suppose sigma is the cycle A1, A2, up to A sub k, and tau is the cycle B1, B2, up to B sub L. They don't have to have the same length. And the A's and the B's are different. AI is different from BJ for all I and J. Right? So what is sigma tau? So that's A1, A2, up to A sub k. B1 up to B sub L. So if I take, for example, an element AI, so what does sigma tau do to an element AI? This sends AI to AI, and this sends AI to AI plus 1, unless it's coming back on itself. And this sends any element Bj to Bj plus 1, and this doesn't involve any Bj, so that's Bj plus 1. And if I take a C not equal to AI or Bj, C goes to C goes to C. And if you check, how does tau sigma act? It's the same thing. Tau sigma sends the tau sigma is B1 up to BL, A1 up to AK. It acts the same way. AI goes to AI plus 1 goes to AI plus 1. Bj goes to Bj goes to Bj plus 1. And C goes to C goes to C. These are exactly the same. So sigma tau and tau sigma are exactly the same functions on the set from 1 to n. So these permutations commute. That's all there is to prove. So if G is a group and H is a subgroup, remember we defined the set of left cosets G mod H is everything in the form XH, X and G. And I could also look at the set of right cosets. And I'll write that as like this, G slash H, H slash G. And one can prove that if you look at the map from this set to this set that sends XH to HX, that's 1 to 1 and onto. So the number of left cosets equals the number of right cosets. So suppose this number is 2. So what can we say? The group has exactly 2 left cosets. So here's the group, and it contains H, that's always a coset, and one other left coset, XH. But the group also contains exactly 2 right cosets. So I have H, and let's say HY. So these are the 2 left cosets, H and XH. These are the 2 right cosets, H and HY. Take a left coset. If XH is different from H, then X is not in H. So in fact, if XH is a left coset and it's not H, then HX, that right coset, is also not H. So G is the union of H and XH. G is also the union of H and HX, which means if I take G and I remove H, HX has to equal HX for all X in the group. Right? If there are only 2 left cosets and only 2 right cosets, it has to be in for a subgroup H has to be normal. If I take HX and HX, if I look at HX and XH and HX, they have to be the same. They're either both equal to h or they're both not equal to h, in which case they're equal to each other. That's a proof. Oops. Problem 17, we take A, an element of the group G, and we define the function f from G to G by f of x is ax A inverse. And we want to show this is one-to-one and onto. So let x and y be in G. F of x equals f of y if and only if ax A inverse equals ay A inverse. But then if you multiply on the left, on both sides, you still have equality. And you multiply by right on the both sides, you still have equality. And A inverse A is the identity. So x equals y. So therefore, f is 1-to-1. And f is onto if for every y in G, there exists x in G, such that f of x equals y. So given y, I want to solve this equation. F of x is ax A inverse equals y. But we want to find x such that ax A inverse equals y. So just multiply on the left by A inverse and on the right by A, and take x to be equal to A inverse YA. So f of x, which is ax A inverse, is A. This is x, A inverse YA, A inverse. These cancel, we get y. So f is onto. Okay. Problem 18. So recall that an equivalence relation denoted by sigma on a set X, it's a relation that satisfies the following three properties. First, it's reflexive. Every element is related to itself. It's symmetric. If X is related to Y, then Y is related to X. And it's transitive. If X is related to Y and Y is related to Z, then X is related to Z. So suppose H is a subgroup of G. We define X related to Y in G if X inverse Y is in H. So that's the definition of a certain relation on the group G. So notice this is reflexive because X inverse X is the identity, is in H for all X in the group, which means X is related to X. Everything is related to itself. This means X, this is true if X inverse X is in H, but X inverse X is the identity, and every subgroup contains the identity. It's symmetric. Why is it symmetric? If X is related to Y, then X inverse Y is in H. But H is a subgroup. So X inverse Y inverse is in H. But X inverse Y inverse is Y inverse X. That means Y is related to X. So X related to Y implies Y is related to X. And why is it transitive? If X is related to Y and Y is related to Z, then X inverse Y is in H and Y inverse Z is in H. But H is closed under multiplication. So X inverse Y, Y inverse Z is in H. But the Y's cancel. This is just X inverse Z. So X is related to Z. So that's the proof that this is transitive. Questions about this? Okay. Moving along. After 18 must come 19. Problem 19 says G equals 6Z. So this is all multiples of 6. And H is 14Z. So that's all multiples of 14. So X is in the intersection, G intersect H, if and only if 6 divides X, otherwise it's not in G, and 14 divides X, which is the same as saying that the least common multiple of 6 and 14 divides X. Let's see, 6 is 2 times 3, 14 is 2 times 7. So the least common multiple, let me call it M, is 2 times 3 times 7, or 42. So if and only if 42 divides X, so G intersect H is the set of all multiples of 42. Right? Something's divisible by 6 and 14 is divisible by 42. If something's divisible by 42, it's divisible by 6 and 14. And what about G plus H? So we define G plus H to be the set of all integers n and z, such that you can write n as a multiple as x plus y for some x in G and y in H. So a number is in G, if it's a multiple of 6, maybe I'll write this as 6a, and something's in H if it's a multiple of 14. So if you look at all possible integers of the form 6a plus 14b, that's what G plus H is. Now you'll notice every one of these is even. So this is contained in the set of even integers. In fact, I claim this is the whole set of even integers because notice that the number 2 is 6 times minus 2 plus 14 times 1 is in G plus H, which means every multiple of 2 is in G plus H. So 2z is contained in G plus H. So G plus H is contained in the even numbers, and all the even numbers are contained in G plus H. So G plus H is in fact equal to the set of all even integers. Okay. Any questions? Oops. Page 20. This is page 16. Problem number 20. Let me write, I'll write it like this, z squared brackets x. This is all polynomials with coefficients that are integers. You know, like you could have f of x equal to 3x to the 4th minus 2x plus 1, or g equal to x to the 10th plus 2x to the 9th minus 7x to the 4th minus 3x plus 1,000. These are polynomials with integer coefficients. And 0 is a polynomial with integer coefficients. And you can just check. Addition is associative, addition of polynomials, and commutative. And the inverse of a polynomial is, like, for example, if this is f, minus f is minus 3x to the 4th plus 2x minus 1. So f plus minus f is 3x to the 4th minus 2x plus 1 plus minus 3x to the 4th plus 2x minus 1, and you add, you get 0. So this is pretty straightforward, just check that this is an additive abelian group. Okay. You can look at 3 by 3 matrices, and this is a generalization of what we saw a moment ago.
So, Professor, the minus f is not inverse, right? It's just another element, like x.
Yeah. So this is a polynomial, this is a polynomial, and this is the additive inverse of this. If you add these two, you get 0.
Okay.
G is 3 by 3 matrices with 1s down the diagonal, 0s everywhere else except in the upper right-hand corner. So you look at all such matrices with integer coefficients in this case. And if you multiply such matrices, I take 1, 0, z, 0, 1, 0, 0, 0, 1, say 1, 0, w, 0, 1, 0, 0, 0, 1. If I do this matrix multiplication, I get 1, 0, 0, 0, 1, 0, W plus Z, zero, 1. And again, this is a matrix which differs from the identity just with some element in the upper right-hand corner. So this set of matrices is closed under matrix multiplication. And if I put minus Z in for W, I would get a 0 here, which is the identity. So every matrix in this set has an inverse in this set. And the identity is just 0 in the upper right-hand corner. So this is a group of matrices, and it's abelian because W plus Z equals Z plus W. What about problem 22? So this is a special set of matrices. It's the set of matrices of the form AB 3CD, where A, B, C, and D are integers. So these are matrices of integer with integer entries, but where the lower left-hand coordinate is the multiple of 3, and the determinant AD minus this times this, 3BC is equal to 1. So for example, if I take A to be the matrix 2, 1, 3, 2, and B to be the matrix 5, 9, 6, 11, we can check the determinant. So each of these lower left-hand numbers is a multiple of 3. The determinant of A is 4 minus 3, or 1. The determinant of B is 55 minus 54, which is 1. So these are both elements of this set. And if I multiply them, let's see what I get. AB, 2, 1, 3, 2, 5, 9, 6, 11. This is 16. 18 and 11 is 29. 15 and 12. 27 and 22. That's 49. That's AB. BA, if I multiply in the opposite order, let's see, this is 10 plus 27, 5 and 18, 12 and 33, 6, and see, 11 times 32 is 352 plus 6, 358. So these aren't even close to being equal. BA is not equal to BA. On the other hand, this G is a group. This proves it's not abelian, but why is it a group? Well, let's see, if you take, first you have to show it's closed under multiplication. But if you have determinant of A and the determinant of B equal 1, then the determinant of the product, which is the product of the determinants, is 1 times 1, or 1. So this G is closed under multiplication. And the identity matrix 1, 0, 0, 1 is in G, because 0 is a multiple of 3. It's 3 times 0. And what is the inverse? So if I take A, B, 3C, D inverse, I claim that's D minus B minus 3CA, and this is in G. Right? I mean, you can check if you do the calculation that this is the inverse of this. So this set of matrices is closed under multiplication and contains the inverse of each element. So it forms a group. Number 23. 23 is another set of 3 by 3 matrices. It's all matrices with ones down the diagonal, zeros below the diagonal, and any numbers at all above the diagonal. So it's all matrices of this form where x, y, and z are integers. And we want to show that this is a non-abelian group under multiplication. So you have to check if you take two elements, 1, 1, 1, 0, 0, 0, x, y, z, or x, z, y, and another element, 1, 1, 1, 0, 0, 0, u, v, w, let's say, that this is closed under multiplication. So if I multiply this, see, what's the first column? It's 1, 0, 0. What's the second column? U, this is u plus x, 1, 0. What's the third column? W plus xv plus z, v plus y, 1. So again, this, when I multiply two matrices of this form, I get a matrix with ones down the diagonal and zeros below the diagonal. So this is closed under multiplication. And how can I get the inverse? 1, 1, 1, 0, 0, 0, x, y, z. So I want to find something of this form. So when I multiply it, I get the identity, right? So let's see. I want to get a 0 here, which means if u is the number here, u plus x has to be 0. So this has to be minus x. For v plus y to be 0, v has to equal minus y. And for w plus xv plus z to equal 0, let's see, v is minus y. So I want to find, what does the w have to be? What does this number have to be? X times v, v minus xy plus z equals 0. So w has to equal xy minus z. So I put xy minus z there. Then this calculation proves that this, the product of these two matrices is this. And you can check by multiplying in the opposite order that you also get the identity. So this is a group. And why is it not abelian? Well, you have to look for two matrices whose product, when you multiply one way, is different from the multiplication, the product you get when you multiply in the other way. So I believe the following would work. If I take 1, 1, 0, 0, 1, 1, 0, 0, 1, and make this a 2. Make this 2 and this 3. So here I write down two matrices, and they both have this property. One's down the diagonal, zero's below, and here above I have 2, 0, 3, and 4, 0, 5. So when I multiply this by this, what I'm going to get in the upper right-hand corner is 10. 2 times 5. And if I multiply in the opposite order, what I'm going to get in the upper right-hand corner is 4 times 3 is 12. So if I call this A and this B, just check, AB is different from BA. So that example, you just have to work it out, will show that the group is not abelian. Okay. And let me skip the last problem because I didn't say what the Klein 4 group is, but the Klein 4 group, it's a group with 4 elements. I can write it as E, A, B, and AB, where A squared and B squared is the identity. And AB equals BA. So this would be, or maybe I can, well, you can think of this actually as the symmetries of a rectangle. If you have a rectangle, there's this symmetry around A, around this vertical axis. There's a symmetry around a horizontal axis, call that B. And there's also a symmetry where you do A and then B. So this, you're interchanging the two diagonals. It's like symmetric through the origin. That would be AB. That's the Klein 4 group. And you can actually think of the Klein 4 group as the symmetries of a rectangle, but I'm not going to talk about that now because it'll take a long time. Okay, wow. So it's a miracle, but I seem to have gone through this entire review sheet. Questions about anything at this point? Remember, I have lots of office hours. I have office hours today at 5 o'clock, Thursday at 1:30. I think I'll have one Friday. I'll add this at 9 o'clock. And maybe over the weekend at some point if there are questions also. Anything else we should do today? All right. All right. Productive day. See you all in person Monday morning on campus at 9 o'clock. Bye all.
Thank you, Professor.